we're going to look at the product rule and just a couple of examples of how it can be used. Okay, so first of all, we're going to just pick an example. So y equals, let's say, x cubed sine 2x. We'll come back to this example in a second. First of all, though, we're going to notice that we could imagine that y represents an area where we have the side lengths as x cubed and sine 2x. And what we want to know is, how will the area change if we change the side lengths a little bit? So you can imagine that we're just adding on a little bit to each of our side lengths. Okay? And what we're going to do is we're going to look at this case in just a second, but for now we're just going to label these as u and v. And we're going to call this extra little bit a small increase in u. You've seen that before when we looked at the small increase in y over the small increase in x, and we said that the limit of that as the small increase in x approached 0. Okay, and similarly a small increase in v. Okay, so what area have we increased this by? Remember, we're looking at how much it's increased by, not the actual area of this new one, just the increase. Derivatives deal with rates of change. So, our small increase in y will be equal to the area of this triangle, this rectangle, which is du multiplied by v, added to the area of this small rectangle, which is u multiplied by delta v. We've also got this tiny little rectangle up here, which is delta u, delta v. Okay, and what we're going to do is now, we're going to say, well, that's how much the area has increased by, but I want to know relative to my change in x. So just remember that at the moment we're calling this function here u and this function here v. U and v could be anything, this will work in a general case. Okay, so I want to know how much y changes by, but with respect to a small change in x. So what I'm now going to do, I'm just going to divide through by a small change in the x value that I'm using. Okay, so now we have a rate of change. How much did that area increase by for a small increase in x? So this is a good approximation, but if I want to make it perfect, I need to look at what's its limit as that small increase in x approaches 0. Imagine that I make these rectangles infinitely thin. So at the moment they're quite chunky, but imagine that I look at what happens as the width of these approaches 0. Well, as you can imagine, as the width of those rectangles approaches 0, it becomes a better and better approximation to the increase in area. And so what we're going to actually get is v, and this is where the deltas change into d's, du, dx, that idealised perfect approximation of the increase in area there. And then I'm also going to get u, dv, dx. And now let's think about this one. Oops, just realised I forgot to divide that by delta x. This term here has two incredibly small changes divided by one incredibly small change. The product of two incredibly small changes is just going to vanish off to 0. So as we look at the limit as delta x approaches 0, we know that these two will also approach 0, and their product must approach 0 much quicker than delta x did. So this will be our formula. If we can differentiate u, that first function with respect to x, and v, the second function with respect to x, I can find out the derivative of y with respect to x. So let's do that. We want to find the derivative. What you'll often find is it's nice to just write down u equals x cubed. I tend to just use a dash to represent the derivative because it's just quicker. So the derivative of that will be 3x, and v dash equals, remember your chain rule, and then actually remember to differentiate it. And then we can just plug in to that formula. Remember, u dash, v dash just means the derivative. So we know that dy dx is equal to, in this case, 3x squared times sine 2x added to x cubed times 2 cos x. Okay, and that's how we can apply the product rule. You differentiate each part of the function, remembering any chain rules, and then do the derivative of u times v added to the derivative of v times u. One more quick example of that. You don't need to go through that whole process every time. This is what you'll probably write down in your exam. So we have y equals some function. Let's go for ln of x squared plus 1 multiplied by cos of 3x. Okay, so just labelling these u and v. Keep the colours. I would then write down at the side u dash is equal to differentiating that with a chain rule times by the derivative of what's inside, and then ln differentiates to 1 over that function. Cos differentiates to minus sine. Remember your chain rule. And then we can just plug into the product rule. dy dx is equal to the derivative of u times v added to, careful we've got a minus there, the derivative of v times u. So minus 3 ln x squared plus 1 sine 3x. Okay, and that's the product rule. It's just a formula you plug into. That's how I would lay it out in an exam.